Hello, my name is Alin Croitoru and I will present together with my colleague Vlad our work, Curriculum DPO, which is a joint work with our supervisor Radu Ionescu, Professor Nicu Sebe and Professor Mubarak Shah. Here is the agenda of the presentation. We will start with a small motivation and preliminary works, and subsequently we will talk about contributions, experiments, and results. We want to efficiently fine-tune diffusion and consistency models, similar to previous works like Diffusion DPO and DDPO. In particular, we want to improve the performance of Diffusion DPO. Diffusion models represent a type of generative models used especially in visual generation. They are composed of two steps: the forward step, in which Gaussian noise is gradually added to the input over capital T steps, and through the reverse process, a model learns to restore the original input by gradually removing the noise. Consistency models are trained via the consistency distillation loss, which encourages a model to produce consistent outputs for inputs that lie at different points on the same diffusion trajectory. More precisely, it minimizes the distance metric between the output of the model for a noisy image xtn plus 1 and the output for xtn, where xtn is obtained by running a denoising step with a pre-trained diffusion model on xtn plus 1. DPO is a simpler and more stable alternative to reinforcement learning from human feedback. Instead of training a reward model and using reinforcement learning, DPO directly optimizes the model to prefer winning examples over losing ones. Here is the DPO objective applied on winning samples IW and losing samples IL. Pi theta is the optimized policy and pi ref is the reference policy. The DPO objective directly optimizes the model to maximize the likelihood of the preferred responses relative to the losing responses. The reference model acts as an implicit regularizer, preventing the policy model from drifting too far. Similar to DPO, diffusion DPO encourages the diffusion model epsilon theta to improve more denoising the winning image XW than the losing image XL. Inspired by the DPO implementation for diffusion models, we propose a parallel adaptation for consistency models. The objective is similar: enhance the model's accuracy on preferred examples, while permitting a rise in error rates for less favored ones. Specifically, given a pre-trained consistency model FREF, we train our model FI to be more consistent with the output of FREF for the preferred samples and to be less consistent with the output of FREF for the less preferred samples. Our second contribution is curriculum DPO. We believe that randomly selecting preference pairs in DPO can be inefficient and suboptimal for learning. Therefore, we introduce a curriculum based on preference difficulty, such that we begin the training with easier examples where the preference signal is strong and obvious, and then we gradually introduce harder examples where the differences are more subtle. This progressive approach allows the model to first capture broad patterns before refining its understanding of subtle preference details. First, we generate images for the set of text prompts that we have. Then, we rank the images using the reward model and generate image pairs ranging from easy to hard. Easy pairs should consist of images that are widely separated in the ranking. Ultimately, we optimize the model starting with the easy pairs and gradually introduce harder ones as the training progresses.
We carried out experiments employing latent consistency models and stable diffusion. We used 3 different reward models for different tasks: cosine similarity of the sentence BERT embeddings between ground truth and caption generated by Lava for text alignment, Lion aesthetics predictor for visual appeal, and human preference score, the second version, for human preference. Accordingly, we have 3 different datasets. Firstly, for text alignment, we use a series of prompts with the pattern subject verb object using animal action object, while for the aesthetics tasks, the prompts are a photo of an animal. 500 images are generated for each prompt. The second dataset is drawbench, and the third one is a subset of 150,000 pairs from pick-a-pick. The baselines we compare to are DPO, DDPO, and the original trained models. Results. As it can be noted, our method has a performance gain in all scenarios. Even in the few cases with marginal gains, the superiority of our method is demonstrated through multiple runs. Here are some results using the first dataset. We observed that curriculum DPO is the only method which generates the beetle and the bike in a coherent picture. Moreover, in the third column, our method is the only one able to generate the butterfly without additional humans around. Fine-tuning for human preference generally results in generating images with more details for the latent consistency model. Curriculum DPO in particular produces better aesthetics for both foreground objects and the background. Here are some other results with stable diffusion with the Lion aesthetic predictor as a real model. A good example showing the increased performance of our method is the camel in the second column. We carried out a human assessment as well, with humans ranking between 4 pictures corresponding to the 4 models, attesting that our method has better results than the baselines. Thank you for listening. If you want to find more about Curriculum DPO, please check our paper and our GitHub page.